Okay, we're going to start with limits, and I always like to intro limits with a little football. So what we're going to do is we're going to pretend that the defense is backed up to the 10-yard line, and they're going to keep getting offside penalties. And everybody knows in football, when you get an offside penalty on defense and you're within 10 yards, it's going to be half the distance of the goal line. And we're going to pretend that this defense is really bad and that they keep getting offside penalties over and over and over again. In fact, we're going to do it an infinite amount of times, or at least discuss that. And we're going to talk about what the football players might say and how that relates to limits. So let's say on the first penalty, they get pushed back to the 5-yard line. But they're really bad, as I mentioned, and they keep getting offside penalties, and they're going to get pushed back half the distance from that point on the next play. Okay, so they're at the 5-yard line, then they're at the 2.5-yard line, and then they're at the 1.25-yard line, which is somewhere over here. Okay, so let's maybe write that. So they started at the 10, they went to the 5, they went to the 2.5, they went to the 1.25. Okay. And it's going to get real difficult to show much more of this, but let's at least go one more. So they're going to go half the distance from there, and they're going to keep getting pushed back. All right, so each time they get half the distance to the goal line. And the question is about this word limits, right? About this word limit. So how does that come up in this example? Well, the defense might be so demoralized, and one of the players may turn to the other player and say, what's the limit? You know, how far can we get pushed back? What's the limit? And the other player will turn to him and say, well, they can't push us back to the goal line, so that's the limit. The goal line is the limit. Now, the important thing here is that no matter how much I go, 1.25, and of course, just keep dividing on your calculator, keep dividing by 2. No matter how many times you press divided by 2, you're never going to get to 0. So 0 is the limit. Even though you can't get there, even though you cannot get a touchdown on penalties, even though half of these numbers each time get smaller and smaller and smaller for infinity, you can never reach there. So the limit is not what you actually get to, but the limit is the place you will eventually reach if you could do it an infinite amount of times, which you can't do. So it's the number you're always approaching, but not actually getting to. Okay, so let's go see what that looks like in math. We have 3 functions here, and we're going to take a look at these 3 functions. The first one is a rational function. The second one's a plain old parabola. And the third one's a piecewise function. Notice that the piecewise is pretty linear everywhere except right at x equals -1, in which case it just has a value of -1. So it'd be a great idea right now to pause the video and see if you guys can sketch these functions first as a good practice and as a good pre-calc review, and then resume the video when you're done, and then I'll show you what they look like. Okay, so I'm going to go to Desmos. I'm going to graph all 3 of these, which I've already done, and let's take a look at all 3 graphs, and then let's talk about limits. Let's talk about limits. Okay, unfortunately, in Desmos, this is a problem because it doesn't show the hole. Hopefully, you guys know from pre-calc there's a hole here, right? Because this is x minus 1, x plus 1. Divided by x plus 1. These reduce, and of course you get x minus 1. So that's a linear function. That's why this looks just like a line. But of course there's one problem, which is x can never be, right? It's really, another way to write f of x is It's x minus 1. It's the same exact thing as x minus 1, except x can never be negative 1, because if it's negative 1, this denominator becomes 0, and that can't happen. So actually, this graph is wrong in Desmos, and not wrong, but it can't show holes very nicely. So we're going to put a hole right here. Okay, so all values are valid along this line except right at this point. X squared minus 3, no big deal. That works fine. Notice at negative 1, it's also equal to negative 2. So it's the same, these two functions here. And the third function also has a problem in that it's a linear function, looks just like this function up here, except h has a problem when x is equal to negative 1. It jumps to negative 1. So when x is negative 1, the h value is negative 1. So there's actually a value here, and this is a hole because this function is not valid at this point. So at that point, this red line has to stop. So what do these three have in common? What are we going to look at? We're going to look at the limit as x approaches negative 1. Okay, so somebody may say to you, just erase this. What happens as x approaches negative 1? What's the limit? Okay, so we're going to write that as the limit of f of x as x approaches negative 1. Okay, so x can approach negative 1 from both sides. We'll talk about left-hand and right-hand limits in a few minutes, but what we're going to do is look what happens to this function as we get closer and closer and closer to negative 1. Now, if you remember our discussion with football, it doesn't actually matter what happens at negative 1. The real value is not important. What happens at negative 1 is not important. What happens as we get closer and closer to negative 1 is important. So let's take a look. Let's go to Desmos. And here's the same function here. It's not really showing a hole here as we mentioned at negative 1, but we know that it's there. So at negative 1, it's undefined, just as we expected. Here it is. At negative 2, it's equal to negative 3. No big surprise. So at negative 2, it's equal to negative 3. At negative 1, it's undefined, which is not displayed here on Desmos, but that we know from our other graph there's a hole there. Well, let's see what happens as we get closer and closer, right? So obviously I can go to negative 1.1. And so at negative 1.1, which is right around here, we get to negative 2.1. Okay, so in other words, a little below negative 2. A little below negative 2. Let's go a little closer, though. Let's go negative 1.01. And you can see, now here you can hardly see that it's different, but it actually is slightly off there if we were to zoom way in, which actually we could do here. Let's zoom way in. You can see it. Of course, you can't see the graph now, but you can see the axes, but you can see it's not quite there. Okay. And let's make it even smaller. Negative 1.001. And we could go forever like this. Okay. And finally, negative 1.00001. Okay. So what's happening? It's getting closer and closer and closer to negative 2. So as x approaches negative 1, the function is approaching negative 2. It's not actually ever reaching there. If we're to zoom way in, maybe that's too far in. It'll never actually reach there. But these dots are getting closer and closer and closer. It's too fine of a distance here. It's getting closer and closer to negative 2.01. Notice there's no negative 2. So if I keep going here, if I go to negative 0.9. Okay, that also doesn't get to negative 2. Even if I make this 9,999. That number's really close to negative 2. That number's really close to negative 2. But there is no negative 2 value here. But that's okay. That's the limit. The limit as -1, as x approaches -1 of this function is -2. It's only true if it approaches it from both sides. So this number here, as you're getting closer from the left side here, is getting closer to -2. And from the right side, it's also getting closer to -2. We'll go over an example where that doesn't happen in a minute. Okay? So back to Notability. The limit as f of x approaches -1 is equal to -2. Okay? It never reaches there, just like we never reach the goal line in football. But the limit, the place you can't get to, but you get really, really close to, and you're approaching forever closer and closer and closer as you get closer to -1 is -2. All right? Now in this function here, I may want to know what's the limit of g of x. Sorry, g of x. As x approaches -1. Now, you might say, yeah, but this actually has a value, right? There's an actual value there. That's not a hole like in this function here. There's an actual value there. Would the limit be the same? And the answer is yes, because we don't really care if it has a value, like this one doesn't have a value at -2, or if it does have a value at -2. That number doesn't matter. What matters is the number that happens when we get closer and closer and closer from both sides. Okay, so let's take a look at that function g of x in Desmos, and let's plug in some numbers. So we're going to plug in -1.1, -1.01, -1.001, just like we did before, but we'll actually plug -1 this time, and it won't be undefined like it was in this function. And then we'll plug in 0.9, 0.99, 0.999. And what we want to see is that both numbers are approaching the same value. So let's go over to Desmos. I'm at -2, of course. -2 is 1, but what we're really interested in is around -1. We're interested in right here, at -1, what's going to happen. So, but before I get to -1, let's go to -1.1. Then let's go to -1.01. And then let's do one more, -1.001. Okay? So as x approaches -1, even though we're not there yet, this number is from the left side here, is approaching -2. It's not quite there. Now, at -1, in this case, we don't get an undefined like we did in the other problem. We actually got a value of -2, but we really don't care about this value because limits don't care about what happens at the number. It cares about what happens as we approach it. So let's go to here and we'll go past -1. We'll approach it from the right. So we'll do -0.999. And you can see as I add 9s live, you can just see it gets closer and closer. But let's do -0.99. And then let's do -0.9. And maybe we'll even go to 0, just to show it on the graph, 0, 3. Okay, so as we approach from the left, which was up here, as we get closer and closer and closer to -1 from the left, we get closer and closer and closer to -2. From the right, -0.9, -0.99, -0.99999, we get closer and closer to -2. But this number can be undefined. It can be -2, and as we can see in the third example, it can be some other number. It doesn't matter. All that matters is that these right here and these right here are all approaching the same number from top and bottom. It's really left and right on the graph, of course. So let's go back and look at the third one for this function. Okay, so we're not going to put this in Desmos, but we're going to take a look at it. So as we plug in numbers, right, so we can make a little table here. So as we plug in numbers for x and get out some numbers for h, So if we put in, let's say, negative 1.1, put in negative 1.1, we get negative 2.1. If we put in negative 1.01, we get negative 2.01. Okay, now I know what happens at negative 1. When I plug negative 1 in, I get negative 1. See, if x is negative 1, then y is negative 1. So there's a sudden jump here, right? Looks like it's approaching negative 2, and then all of a sudden it jumps to negative 1, right? It jumps to negative 1. So it was approaching negative 2 from here, and then suddenly it's at negative 1. But if I go just a little past it, right? Negative 0.99. If we plug in negative 0.99 in for x, we get negative 0.99 minus 1 is negative 1.99. Okay, and of course if I put in negative 0.9, I get negative 1.9. So as you can see, right, from this side, from here, as we get closer and closer, it's getting closer to negative 2. And from this side, from here and then to here, we're getting closer to negative 2. And notice I don't care what happens here. Even though it made a jump, it could have jumped to 0 or it could have jumped to 8. Even though it made a jump, the value at negative 1 is not what's important. What's important is, what is the value as you get close to negative 1 from both sides? And they're both approaching the same number. From the yellow here, we're approaching negative 2. We're not quite there yet. And from the green, we're approaching negative 2. So this definitely has a limit. So the limit as x approaches, but never reaches, negative 1 for h of x is equal to negative 2. And this was negative 2 also before. Okay. The next example we'll look at is when something doesn't have a limit. Okay, so let's look at our fourth example, and let's see what happens when sometimes we don't have a limit. Okay, so in problem 4 here, what we're going to do is we're going to explore, so problem 4 is a piecewise function, and we're going to explore what happens when the limit, when someone asks us for the limit as x approaches 2 of this function. Okay, what happens, what's the limit as x approaches 2 of I? Well, this function is a linear function, x plus 1, all the way up to and including 2. That's why there's a solid dot here. But once you go above 2, so 2.001 or 2.1 or 3 or 4, right? Any of those x values produces a value of 4. So we have a jump. Discontinuous, excuse me, and it's a jump. So what happens when someone asks us for a limit? Well, if we make a quick table here of values and we take a look at all of the x values from the left. Sorry, that's not going to work, so let's make a nicer table. And we want to plug in some values for x and see what we get out for I. So let's plug in negative 1, negative 1.9. We'll see what happens at 2, although we don't really care. And then we'll do 2.01 and 2.1. Okay, so at negative 1, we get 0. Oh, sorry, that's supposed to be positive 1, my bad. At 1, we get 2. At 1.9, we get something close to 3, right? 1.9, we get 2.9. And at 2, we get 3. So at first glance, without checking the other side, we may say, oh, look at it, it's approaching 3, right? Again, I don't care what happens here. That number doesn't matter to me. But as x gets closer to 1.9 to 2, so 1, 1.9, 1.99 would be 2.99. All of these numbers are getting bigger and bigger and bigger, but never reaching 3. So getting close to 3. But let's see what happens on the right side, because remember we talked about limits have to be approaching the same number from both sides. Okay, so we put, 2.01, which is somewhere right about there. And what is the y value? Well, according to this, when x is greater than 2, the y value is 4. At 2.1, somewhere around here, right? The y value is also 4. If we were to keep going, even to 3, the y value is 4, etc., right? So the point is, from the left side, it's approaching 3, but from the right side, it's not approaching 3. It's approaching 4. So it has no limit, right? Or DNE does not exist. Okay, so it has no limit as x approaches 2. Now, what happened is we actually looked at it from the left side and from the right side, and we got two different limits. So we actually have notation for what we call left-hand limits and right-hand limits. Okay, so let's do a left-hand limit. And we write left-hand limits, right, like this. So they're not real limits, they're just partial limits, but it's not negative power, it's just 2 from the left, right? So there's negative sign. It looks like the power is negative, but it's just 2 from the left of this function I of x. Okay, and then a right-hand limit. We actually did these for the previous examples. We just didn't name it, right? And we didn't use this notation. We just looked at it from both sides and saw that it was approaching the same thing. So this one is approaching 2 from the right side of I of x, okay? So we have, the left-hand limit here. And then we have over here the right-hand limit, okay? And they both have to be the same in order for there to be a limit, right? In order to be a limit. Okay, so the left-hand limit says, as x approaches 2 from the left side, right? So from the left side, that would be 1.9, 1.99, right? So as it approaches this point here from the left side, so all of these points here, right? They're getting closer and closer to a y value of 3, or in this case, an I value of 3. So as we get closer to 2 in the x direction, as x becomes 1.9, 1.999, we're approaching 3. So we say the left-hand limit is 3. It doesn't actually get there, right? As we approach 2, as we never get to 2, it never gets there, but we know it has a limit of 3. It's getting closer and closer to 3. Now from the right side, what happens? Well, all of these points, as we get closer and closer and closer to 2 from the right side, so 2.2, 2.1, 2.01, is approaching the number 4. They all have values of 4. So we say the right-hand limit is equal to 4. So if I ask you this, in this notation, there are actual answers, but there's still no limit at x as x approaches 2, right? Because these aren't the same. So that's why we get DNE for the general question, what's the limit as x approaches 2? So these are just partial limits, right? Left-hand and right-hand limits. And they're just really used to determine, do we have a limit or not? And in this case, we don't. Now, the one thing I want to make sure we don't get too confused about is this function does have lots of real limits, right? So for example, what is the limit of I of x as x approaches 4 equal to? Okay, well, if we go to 4, which is right here, okay, we don't look at that point, we don't care about this point, but let's look at 3.5, 3.9, right? So at 3.5, 3.6, 3.7, 3.8, 3.9, all of the y values are approaching 4. So the left-hand limit, I'm not going to use the notation, but if I was to put a negative sign here, right, the left-hand limit would be equal to 4, right? And the right-hand limit, I know I said I wasn't going to do this, but I'm going to, as x approaches 4 from the right, is also 4. Okay, so then back to the original question, does this have a limit? The answer is yes. So really, for any other value anywhere on this, as x approaches 3, it's still, the limit is 4, right? As x approaches 1, as x approaches 1 from both sides, the limit is 2. Okay, and as x approaches, let's say 0, so as x approaches 0, the limit is 1. So there's plenty of places where it does have a limit when these left and rights do match. But at this one particular value, x approaches 2, this function does not have a limit.